Thanks. Hi, my name is Jim Delling, as DT said, and I'm going to talk today about real-time machine learning. I'm going to talk about it in the context of a platform that we developed called Hopsworks. Hopsworks is a feature store primarily, but it also has integrated model serving capabilities through Kserve. I'm going to talk primarily about real-time machine learning and how we can build real-time machine learning systems with Hopsworks. But why do you want to build real-time machine learning systems? Well, if we look at this diagram here, we see business value on the y-axis, and on the x-axis we have the ML machine learning operational capabilities you need to have to generate business value. Now, after you have your data house in order with traditional analytics, you may consider doing machine learning. Think of this as being a hierarchy of needs. You need to first have your data house in order to start working with machine learning. So typically what companies will do is they'll identify a prediction problem that they want to address. Maybe you're going to build a recommender service that we'll talk about today, or maybe you're going to use it for churn or identification of customer value. There are many different prediction problems you could have. So firstly, you'll need to start collecting some training test data, maybe doing some analytical machine learning, so running predictions on batches of data on a schedule. So we call those offline predictions. And if you're able to generate business value and you see opportunities to build operational machine learning systems, that means machine learning systems that run 24/7. Maybe it's a user-facing system, maybe it's a website for e-commerce, or maybe it's a user-facing service. Then you have the question of, well, how do we get the data to this operational machine learning platform? One way you can do it is with batch updates. You can have some data that you make available for the predictions, not just the model itself, but we'll also need history of users visiting the system, the context of what is maybe popular right now, what's trending on the system. All that information is what we call features that we'll need to make available to our models at runtime, so in real time, in order to be able to make richer predictions. So you can make that data available through batch programs that make periodic updates, but you can also do it with real time. So real time means taking data that with as low latency as possible, making it available to the models to make predictions. And if you think of the highest kind of value AI systems out there today, I think TikTok would be one of them, by ByteDance. And TikTok is very well known for its recommender system, which is very addictive. So Andrej Karpathy called it digital crack. He was the head of AI at Tesla for quite some time. So, the reason why it's very addictive, TikTok, is because it adapts to your preferences as you browse. So it looks at how long you spend on each video, maybe what you're searching for, what other people are watching right now, and all that data is integrated into a single place so that it's made available in real time so that you can build very high value real-time machine learning systems. So the technologies you need to be able to get there for offline prediction are batch programs. So maybe you can have Python or Spark or SQL. For online inference, you can have batch programs updating the data, but for the very highest value, you'll need streaming features. So that means streaming pipelines, feature pipelines, technologies like Spark streaming, Flink streaming. We're not going to talk too much about streaming feature pipelines today. You can take that another time, but Hopsworks as a platform supports streaming feature pipelines to update their features in real time. What we'll also talk about today is how we integrate our real-time features with models that we're serving in production. So we call that those deployments. And if you have a deployment that needs maybe the history of users or the context in which predictions are being made, you'll need to connect it to something called the feature store. And the feature store is really a data layer for your machine learning models. It enables you to store pre-computed features. If you have a user, maybe you're going to know information about how many times the user has visited in the last hour, the last week, maybe the last month. If it's an e-commerce site, are they a high value customer? Maybe you have session data related to the user as they've been browsing through your page. And you'd like to make all this data available to the models, and you can do that through this data platform called the feature store. So the feature store can provide data both in what we call offline or online mode. I'll go into some details about that. Online is for real-time models, so models being served, and offline are for batch programs. So programs that are going to run on a schedule, make predictions with a model, and then they'll turn off when they've made their predictions. Okay, let's have a look at the architecture we're going to discuss today. And this is a complete architecture that will enable you to build real-time machine learning systems. I'm actually going to extend it somewhat today. I'm going to introduce a recommender system, a real-time recommender system. I'm going to add an additional service called a vector database. But the core of what you need to build a real-time machine learning service is you need data that we have on the left-hand side. So we can see we have a data warehouse. You might have event bus like Kafka or Kinesis with real-time data arriving as events. You may have applications generating data, and that data will need to flow into this platform called the feature store, where we're going to store these pre-computed features and make them available to our models. Here we have models deployed on a model serving framework called Kserve, which is Kserve is pretty much the de facto open source model serving framework for Kubernetes. And Kserve will manage your models and take requests from online applications, make the predictions, but it can also be integrated with a feature store to retrieve pre-computed features at very low latency. So models that are deployed in production will need a model registry. So we'll look at the model registry in Hopsworks. And then as you're building probably an enterprise platform, you'll need a lot of enterprise features, such as the ability to version features, look at statistics for them, the code used to compute features, and lineage, knowing when a prediction is made, being able to find out, well, where was the data come from that prediction was made from. Okay, without any further ado, let's jump in. And if you have questions, just shout them in the chat. So we're going to look at first the feature store. Now, I mentioned already that the feature store can be updated either with batch applications or with streaming applications. So in Hopsworks, a feature group is a table of features. Typically, it will be stored in the platform. So if it's made available for real-time API, so there's something called the online API where you would like to read features at low latency, it's stored in an online feature store, an online database. We have a platform called RonDB, which is a fork of MySQL cluster. And if your data is stored offline, Hopsworks feature groups can store the data internally as hoodie tables, Apache hoodie tables. But you can also have external feature groups. Maybe you have Snowflake, or maybe you have Databricks, or just Parquet files in S3. They can be made available as feature groups as well in Hopsworks without having to copy the data in. Now, the two APIs for reading data from the feature store in Hopsworks are called the online API and the offline API. Now, the way in which you read features in Hopsworks is you create something called a feature view. Now, the feature groups are our tables. That's where the data is actually stored. But when you want to create a model, you want to train a model because you'd like to solve a prediction problem, you need to select features from the different feature groups. Typically, they'll be from more than one feature group. And what you do is you create a feature view. It's a logical view. Think of it as being a database view over maybe different columns or tables. And it's metadata, so there's no data stored in it. You create it, and then from it, you can read data offline if the backing feature groups are available offline, and online if the backing feature groups are available online. Now, once you've read your data, and maybe if you're going to train a model, you're going to read from the offline API. If you have a smaller model, maybe with data frames, if it's a larger model, you might have files that you're going to train your model with. But the model needs to be registered in a model registry. Now, Hopsworks has a model registry built in. Many people use platforms like, well, I'm trying to think of the top. SageMaker is a popular model registry, and Databricks have a model registry, MLflow, which is available open source. And then you have Weights and Biases, which is a managed service. So Hopsworks is available. I should say at this point, it's also available as a managed service. So everything we're going to talk about today, you can create an account for free. If you want to do it in the background, I'll just tell you now while I'm talking, you can go to, I'll just put a link in the chat if you're curious while I'm talking. It's www.hopsworks.ai. You'll get storage space for 25 gigabytes of data, and you'll be able to store hundreds of feature groups, and you'll be able to even host up to two models concurrently deployed, and many online features as well. And there's a model registry, which is, I think it's unlimited number of models up to your storage capacity. So the model registry in Hopsworks allows you to store your models, but models by themselves, if you train a model in scikit-learn, you might need a Python, what's called a predictor script. So you wrap your model inside this Python program. TensorFlow models can be deployed on TensorFlow serving servers. You don't need necessarily predictor script. And in Kserve, which is the model serving framework I'm going to introduce, there's also a component called a transformer. So before a request is sent on for prediction, you might want to perform something on the inputs. You might want to have on-demand features computed. You may want to go to the feature store to retrieve pre-computed features, and those actions can be performed in the transform. It's a Python program that will be executed before the predictor, which contains the actual model that makes the prediction. So the models in a model registry, you may have other artifacts that you need. You may have these on-demand features that you need to use, so it could be code. You may have other files that are needed for model serving. So once you have your model in a model registry, then you need to be able to deploy it in order for online applications to be able to make predictions over the network. So you need a model serving infrastructure. I mentioned Kserve is the one we'll talk about here. Other popular model serving frameworks are SageMaker and Databricks. So your prediction service that makes predictions, typically it might expose an API, or maybe it's user facing, but when your model is being deployed, requests can come in over the REST API, secured of course, and they'll provide some parameters. Maybe you'll need to know something like the identity of the user, because you're going to go to the feature store to look up pre-computed features for the user. And maybe there's going to be some raw data that comes in that we need to compute on-demand features from. So typically then the model server will take this model that's deployed, it'll perform the transformation, the prediction and return, but of course you want to instrument this model serving server. So it will generate logs. Those logs will have value, not just for operating your model in production, being able to debug it and find problems, but also those logs can be used to generate potentially new training data for services, because users are interacting with your service. In the recommendation example I'm going to go through today, if you recommend something to a user and a user selects an item, well, that's training data. And if the user doesn't select an item, that's also training data because the user didn't select it. So these inference logs can be very valuable, and you want to capture them so that you can create more value from your online interactive systems services. So backing all of this, of course, you'll need enterprise support for versioning all of the ML artifacts we have here. So the artifacts are features and models. You may want to perform experiments on top of your training layer, and you may have, you probably will want to deploy models with A/B testing. So being able to support things like canary deployments and A/B testing in your serving is important, so that you don't deploy a model that performs poorly for all of your users. You might start at 1% of the users, and if it works well, then roll it out to more and more users. So let's look a little bit at the pipelines that make up this production ML service. And really there's 3 pipelines in total. And those pipelines are feature pipelines to create features from our incoming data. So we may have, for a streaming application, we have data coming from Kafka, a data warehouse, you have application data that you've captured. And these pipelines, typically they're programs written in SQL or Spark or Python or even Flink, and Hopsworks supports all of those types of feature pipelines, and they'll write to these feature groups. So in Hopsworks, they write a data frame, either in streaming or in batch. You write a data frame to the platform, and that data frame is stored and appended to the feature group. So feature groups, the tables, are mutable. They're appended, they can be updated, rows can be deleted. And we have what we call time travel, the ability to look back in time and see what the feature group looked like at a previous point in time. Now, when you want to train a model from your features, you have to create a feature view first. And from the offline API, you'll get training data. So a training pipeline will go to the feature store and say, hey, I would like some training data. Maybe it's going to be a pandas data frame. If it's large data for TensorFlow, it might be TF record files. But with that training data, you train a model, and the output of a model is a model stored in a model registry for a successful training run. There is a batch API, sorry, to the feature views. In what we look at an example later on is being able to get batches of feature data. So for example, I'm going to look at a recommender system that can recommend items in an e-commerce store. So we might like to say, okay, I want to read all of the items in the feature group with the items. And I'd like to, I'm going to create embeddings for all of those items. And I'm going to store those embeddings in my vector database down here. So that's what's happening there. Now, once you've trained your model and you deploy it, you can deploy it to make it available as a batch application, in which case it can read more data again from the offline API. So it'll say, give me all of the data maybe that's arrived through the feature pipelines in the last day, and then it'll score that data and store the predictions in some downstream database or some sync where applications can pull out the results. And sometimes the sync is an operational platform. So for example, Spotify Weekly will do this big batch application that once a week updates your playlist, your weekly playlist. It's a batch application, but you as a user once a week get some recommendations. It's nice. But the online applications, that's the TikToks, these are running 24/7. And when they need to make predictions, they're going via the online API to the feature view, getting back features within milliseconds and putting those features together to make feature vectors to make predictions with. So that's the three pipelines: our feature pipelines, training pipelines, and inference pipelines. Now there's a little bit more detail around those that you can see it's been added to the diagram. We can see, for example, that your model registry models have the schema, they have versions. Features are also versioned, and feature groups have a schema as well. So the schema has a version, but actually the data that's written as well. So you get commits for the data written to feature groups. We call that data versioning, is also supported here. Feature views, again, can have a schema and can be versioned. You might have a first version of a model. It has a certain schema, and then you try version number 2 of the model where you've dropped some features or you've added some features that are, or changed the implementation of features, so you have a breaking schema change. Well, then you create a new feature view with a different version, maybe the same name because it's the same model, but a different version. And when you train that new model, you'll have the new model and its version in the model registry, and you'll deploy it in the model serving server. Now, there are some other things that are interesting in Hopsworks. Feature views also support transformation functions. So typically the data, the features that you store in the feature tables or feature groups, we don't often perform what we call model-specific transformation. So if you have a numerical feature, well, and you know that it follows a long-tail distribution, should I use a min-max scaler on it? And that's useful if you're using a gradient descent model training algorithm. But the problem is if you do that before you store the feature in the feature group. So if we encode this numerical value with our min-max scaler, well, then the features are, firstly, they're computed using the min and max values when you wrote the data or from the data in the feature group. And when new data arrives, those min and max values change. So you need to recompute all of the data in the feature group. So that's not good. The second point is that you may have more than one model using those features. Maybe one is using TensorFlow and another one is using XGBoost. So the XGBoost model won't want the data transformed. It doesn't want this model-specific transformation. It doesn't need it. So it doesn't need to transform the numerical feature to help it converge better, but the TensorFlow model does. So in that case, the feature group data that you write, the features, model-specific transformations will typically happen after the feature group. So the way we do it in Hopsworks is that each feature view, which is model-specific, you can attach transformation functions transparently to them. So you can say, this feature this categorical feature, I'd like to use a label encoder. This numerical feature, I'd like to use min-max scaler or logarithmic scaler. And then these transformations are performed transparently to you. So when you retrieve the data from the offline or online APIs, those transformations are executed in line as Python UDFs. A little bit technical points. Okay, let's jump and look at some of the data flows that we have here. So through the offline API, we get our batch data. In this case, we can see a batch inference job. It's going to retrieve batches of data from the offline API. It'll make some batch predictions, and then we have an application that will consume those predictions. For a prediction service, an online application, it'll use the online API to retrieve recent features. In the case of the recommender system I'll look at later, we may want to use embeddings that we're going to compute. So we're going to compute embeddings, we'll put in some data, compute embeddings, or retrieve features that we're going to use embeddings for. And then in Kserve, when we're making predictions with our predictor and transformer, the logs that are generated, there's something called an inference logger that we've implemented in Kserve, which can take the inference logs and make them available so that you store them back, for example, in the feature store. And the online applications will use these online prediction services to make predictions. So if we make it a little bit more concrete in terms of what is stored in these different components. So the features are stored into feature groups. Here we can see this feature 1 is stored in feature group 1, feature 2 is stored in feature group 4, and so on. So we can see here that feature groups also have a primary key, because when we want to retrieve features from a feature group at runtime, we'll often need that primary key. Maybe it's going to be the user identity and say, well, here's the user, give me the most recent feature values for this user. So streaming feature pipelines can be used to update these features, which ultimately write to these feature groups or tables. The feature view represents the model effectively. So if I have 3 models, I may have 3 feature views. And we can see here, we have a transformer in our model serving server and a predictor. So this is a model that's deployed. And what we want to do in this particular case, this is a more complex case, but what we want to basically do is say, okay, in my transformer, a request goes in to make a recommendation for something. So I'm going to go to my feature view and get out the features for the user who wants to make the recommendation. And then I'm going to go with that, I'm going to compute an embedding for that user and the query that the user had, and use something called similarity search from my vector database to say, well, show me the items that are similar to this user query, that match this user query. So with that, I can take all of those items and I can find new features for them and make predictions to rank. In this case, we're going to look at a different model to rank the different candidate recommendations. We'll look at that in a second. So ultimately, yeah, you make your request for the recommendation, and then it goes from the transformer to the predictor and back to the online application. And there's a lot, we can see a lot of back-end traffic happening there. So I'm going to go into a little bit more detail now about this specific use case, real-time personalized recommendation systems using the Hopsworks platform. All this code is available on GitHub. It's in Hopsworks tutorials on our GitHub page. But let's jump in. So what I'm going to look at is starting on embeddings. I've mentioned embeddings already, but I haven't defined what embeddings are. So an embedding is you take some very high dimensional data, and if we take a user who's making a search, so we're trying to build a recommendation system for a user. The user has entered a search into a web page. We take that data. We'd like to combine it with lots more data. We combine it with all of the information on the user's session. What pages have they visited? What links have they clicked on? What else have they searched for? Maybe we have the history of the user. What have they purchased? How much money have they spent in the last month, the last year? Their profile, what preferences are they? What other features about their static profile, where they live, and so on, can we use to help make predictions? So altogether, all of this data, there can be quite a large amount of data. So what embedding can help you do is take all of this large volume of input features and compress them. So the embedding itself is a machine learning model. So it's a deep learning model. It's an encoder from the autoencoders. And what you do is you train this model. So you train this user encoder model and you put in some input, the user's current search and their features, and you get back an embedding. And the embedding is it's an array of floating point numbers, and it has a dimensionality. So maybe it's 64 floating point numbers, or 32 floating point numbers, or 200. But basically, that's the dimension of our embedding. So the number of elements in the array is the dimension of the embedding. Now, what's pretty magical about embeddings is that they retain what we call semantic relationships from the input data. Now, here's an example of if we took all the words in English, so there's something called word2vec, where you take a word and you compute it and you transform it into a vector or an embedding. And with the embeddings that we have, if you take the word man and you say, okay, man minus woman, and you'll get this vector here. And then if you applied that vector and said king plus man minus woman, you'll get queen as an answer. So the relationship between these is retained in the embedding. It's quite amazing. And here's some more examples here. So if you trained a model, you can do with similarity search. You can say, well, Turkey is to Ankara as Russia is to what, and you would get back Moscow. And the same here for verb tenses. So embeddings are pretty powerful. But what's really interesting about embeddings is that the example I gave you there is just for a single modality. It was just for words. Or countries and capitals and so on. But what if I have two different modalities? And the modalities that we care about in recommender systems are the items that you're searching for, and then the user queries and the user's history. So if we took the user's features, the user's query and their history and the context, can we find an item that is relevant for that user query? Now, these are two different embedding spaces. You have the embedding space with the items, where you take all the items with their features, compute the embeddings, and create that embedding space. And you have another embedding space with the user queries. And there'll be two different embedding models. But can we join them together? And the answer is yes, you can. And you need to ground them by having the interactions between the user queries and the items. And effectively what this means, it's a technique called two-tower model. And effectively what you need to do is you just need to have the user queries and the item interactions stored as your training data. So what that means in practice is that if you have a website where you are allowing users to search and you return some items, here returning items 1 to 4, and the user maybe clicks. So the user clicks, in this case, on item number 2, and we give it a score of 1. So the user clicks on item number 3, but maybe adds it to the web basket, so your shopping cart. So maybe we give it a 5, a higher score, but the user didn't click on item 1 or item 4, so they got a score of 0. So you can log or instrument your website, if you have an e-commerce website, to store all of this as training data. Now, this is the key training data to train two-tower models. It's also training data that we use to train a ranking model that we'll talk about in a little bit. So if we have the interactions between the user queries and the items, we'll be able to train a two-tower model such that we can take user queries and map them into the item space and say, this is the most relevant item for your user query. Now you can do the same. This is for recommender systems. You can do the same for personalized search. So if people are searching for things, not necessarily recommending them, you can also train very similar models. So it's a very powerful paradigm. So the way that you train a two-tower embedding model is that you take these user item interactions as your training data, and you train the two models in parallel, the user query encoder, which takes all the users' features, their preferences, their history, maybe what's trending, and then the items themselves. So the items may be, if it's an e-commerce site, they'll have a category, they'll have a price, a popularity, availability, and so on. And you train an encoder. So the encoder is what it's trying to do is just put in an item and compute an embedding such that it retains as much information as possible from the original set of features. The idea with encoders, autoencoders, that you can recreate the original input from it. So you're not supposed to lose much of the information, but you're compressing it into this array of floating point numbers. Now, with both of these arrays of floating point numbers, now they have to be the same dimensionality. So they have to be, if we have 52 arrays in the embedding here, so the length of the array is 52 for a user query, it has to be also 52 for the item embedding for this to work. Now, the way it works is that we put in our input training samples, and the training samples have a label, and the label is the loss here. And the loss in this case is 1 if there's an interaction. So if the user clicked on this item, we saw earlier that you can have like an even higher loss. You could have a 5 if the user bought the item as well, and 1 if the user clicked on it, and 0 would be non-interaction. So you can have different loss functions here, but typically the loss function that's most popular is the dot product. So the dot product will compute the difference between them, and that loss will then be fed back to adjust the weights in both of these models. So your sample comes in here through both of these parallel or two towers. They compute the embeddings, and then we compute the loss, and then we use that loss and automatic differentiation to update the weights on the different models. Now, luckily, the code for that is pretty straightforward. There's, and I'll show you some code from TensorFlow recommenders. But the way you train the model then is basically you need to create these training data sets for the two-tower models. So in Hopsworks, in the code we have some feature views. So the items, we have an example which is based on Hennes and Mauritz, or H&M. They have released a recommendation data set. So they have items in there, they have users queries that and then the items that users clicked on. So they end up being different feature views and feature groups in the platform, and we can create training data from that. And with that training data, we can train both our user query embedding model and our item embedding model. What we'll also need later on is a ranking model, we'll see. And in the code, we train the ranking model as well. So we'll end up with 3 models that we store in the Hopsworks model registry. the embedding models for user queries and items, and then the ranking model. Now, what we're also going to do is the items themselves, we're going to store in a what's called a vector database. And Hopsworks has support for a vector database called OpenSearch KNN. It's an approximate nearest neighbor index. And what you can basically do is take all of your items. Once you've trained this item encoder, so this is our item embedding model here, and we can have a batch job that reads up all of the items, computes the embeddings, and writes them to this index. And what it's writing is the ID of the item, so the unique ID of the item, so that we can look it up later, and then the embedding for that item. So what we'll be able to do with that is do similarity search. So if we build our embedding space, so we have this job building up the embedding space. Here, the embedding space are book names. They're Shakespeare books and other books. And the user then comes with a query, and they say Shakespeare tragedy. And you can see here it maps the closest books are Romeo and Juliet and King Lear, not Pride and Prejudice or Great Expectations. So that's basically how it works. You train your both of these models, and then we build the embedding space for the items. So this is in our vector database, or KNN. And then when we've built this embedding space, we can then use queries at runtime and say, well, the user searching for Shakespeare tragedy, here are the best books, Romeo and Juliet and King Lear. So that's basically how the two-tower network works. We have this mapping from user query space to item space. Now, when you put it all together, what you end up is an architecture called retrieval and ranking for personalized real-time recommendation systems. It's quite a long title, but they're called retrieval and ranking architectures. What you're basically doing is users enter queries, and then we take all of the features as well, not just what the user entered in the string, but all the other information, the context and history that we have to compute this user query embedding. And then we go to this vector database, OpenSearch KNN, and we get candidates back. Now, if you're an e-commerce site with tens of millions of items, you're not going to return that many. You're going to return maybe a couple of hundred, maybe 200, 300 items. And then those items, we call them candidates, because one of the issues with the candidates that you get back is that you can imagine that often they're going to be very similar to one another. If users are always recommended the same things, then users might lose interest. So you want to ensure that when the items are returned, that you order them in such a way that maybe you maximize revenue from the users, or maximize the chance that they'll put those items into a shopping cart. So ranking models help you there. They help encode policies, such as maybe you want to have some diversity in the rankings, not just the optimize for the closest ones in embedding space. And one thing that you can do with a ranking model is you may get your 200 candidates back here, but to build a ranking model, we only had, if you remember, we looked here earlier on, we just insert the item ID and the embedding. So all we're going to get back are the IDs, the unique ID for all the items. We don't have any features for the items. We may have the user's query, but we're not able to personalize these candidates that were returned because we just have their IDs. So luckily with the feature store, you can make a lookup and say, here's my 200 candidates, here are the IDs for them, and you'll get back the features. And in Hopsworks' case, we have some nice benchmarks with Spotify where we return about 250 primary key and 10 features back in under 30 milliseconds. So the P99 latency is less than 30 milliseconds to return all 250 rows containing all the features for the candidates. So it's very quick. Typically you use a low latency model like a gradient boosted decision tree, and then within maybe 10, 20 milliseconds, you've ranked all of your candidates and you can return the ranked items. And trends and feedback, you can feed back into the feature store. So what this kind of looks like when we put the user in the picture is that the user wants to recommend something. Maybe they've clicked on, they've finished watching a series, and then we use the most recent thing that they watched as the input, the main input, and say, okay, what should I recommend next? This was the last thing they looked at. And then we take all the feature related to their viewing history and recent history and the context of what's good or not, and we compute this user embedding. And that can use the feature store. At this point, we can actually retrieve many features from the feature store to create the user features for the user embedding. Then we go to our approximate nearest neighbor search algorithm. So it's going to use a vector database to retrieve the candidates, the items that are closest using similarity search. We're going to go to the feature store to enrich those items that were returned with their features. And then we'll rank those features and return the ranked features to the user. So all of this should happen in less than 100 milliseconds. And you can see there's a lot of traffic happening at the back end. So you can see that if we overlay here now the services, the operational services you need to implement an architecture like this, and this is in the case of Hopsworks, we have three main components. We have the feature store, which provides the online API to retrieve features. We have our models deployed on Kserve, and then we have OpenSearch KNN as our vector database. So when the user comes in at the beginning to start a recommendation request, we're going to retrieve user features from the feature store. We're going to use the model deployed in Kserve to compute the embedding. Then with that particular embedding, we're going to go to OpenSearch KNN, retrieve the candidates. Then we're going to go to the feature store to retrieve all of the features for those candidates. And then with the ranking model, we're going to rank all of those candidates. And then we'll finally return those to the users. So there is a little bit more you can do in here as well. You can also add an additional stage here called filtering. So often maybe candidates returned in particular, if you're recommending in e-commerce, you may want to not recommend items for users who are not adults. You don't want to recommend them to children. Maybe items are sold out. Maybe users bought an item before or it's not available in the user's region. Then in this case, you shouldn't return those candidate items to the users. Users will get a bit annoyed, of course. And then you want to ensure maybe some diversity. You can pick random, you have some random candidates thrown in there as well. So I'm going to do a little demo and we'll have a look at this particular architecture at this point. So let's have a look at firstly, if you're curious, this is Hopsworks.ai. You can create an account here, it costs nothing, and it's time unlimited. We're not going to, it's like, think of it as being like Dropbox or Trello. You get a free account and you'll be able to use it, time unlimited. So I just create a cluster here. So Hopsworks is also available open source and as an enterprise platform. Kserve is only available in the enterprise platform, not available in the open source platform. In that case, models are just served as Docker images or Docker containers, sorry, on the Hopsworks cluster. But in the enterprise version, it's integrated with Kserve. The managed or the SaaS version here does have Kserve capabilities, so you'll be able to use it in there. Okay, let's have a quick look at the artifacts that were created. I'll go through the code in a second, but we'll just look at the artifacts. So this is the H&M use case. We have three different tables of features. We have the customers, and these are the users you can think of. There's not that many features, and you got the ID, their age, and postal code. In Hopsworks, you can see how they're used through the provenance, so the feature views that they're used in and trained data sets created. In Hopsworks, we also are able to support great expectations. So if your feature pipelines validate the data getting written, we'll see the results in here, and we can have tags for searching for them and alerts if, for example, there's a problem in your feature pipeline. We compute statistics on the data as it's written in, so you can get an overview, so good for EDA. And you can also preview the data, so you can have a quick look at some of the data that's in there. So you can see the ages of the users here. And you can see this is online. I'm looking at the data. You can also look at it offline because the data can be stored both online and offline. And then we've got articles and transactions and so on. So these are the clicks. So when users clicked, here's a customer who clicked on a particular item at this particular point in time, and then we have the price of the item. The channels, did they buy it in the store, was it online, and then the timestamp when it happened. So these are the tables that were created. We've got the articles themselves, the items. You can see there's a lot of features for those. So what we want to do is we have pipelines to update them. So let's have a quick look at a pipeline, a feature pipeline for getting that data. And this is the feature engineering part. You can see they come from CSV files. Now in a production system, they'll probably come from a data warehouse and be updated daily. And in a real-time pipeline, so if we have a streaming feature pipeline, they'll probably come from Kafka or Kinesis. So in this case, we're just taking them as static data. We log into Hopsworks, and then we read up our data frames These are pandas data frames. And we do some feature engineering. So here we've done some very basic feature engineering here. And what you want to do then, once you've done your basic feature engineering, here we're trying to transform some dates here. And what we're going to do is write them as the tables or feature groups. So you create your feature group, you identify which column in your data frame is the primary key. In this case, we want them to be available online as well. So we're going to say online enabled, and then we just have a name and a description for the feature group. So all you need to do then is insert your data frame, your pandas data frame, into the feature group, and it'll get written in there. And we do the same for the 3 different feature groups. The articles, we take our data frame for that, and then the transactions, these are the interactions between users and items, we write those as well. So what we can also do then is create feature views, because we want to read from these different feature groups. So we can have a feature group for just the customers if we want to read that, or the articles. And in the next notebook, we also create one around the that takes features from the many different feature groups. So this one, you can see that when we do feature selection, we're able to use a pandas-like syntax to say, I would like the customer ID, article ID, TDAT, month, SIN, and month costs from the transactions feature group, joined with the age of the customer from the customers feature group, joined with features related to the items, the garment group name and the index group name. So this is basically then going to be the training data. We're going to use this query object, selecting the features to create a feature view. Before we do that, we're going to say some of the features we're going to transform. So we have these model-specific transformations that we'd like to define. So in this case, we're you can see here that we've got a pre-made transformation function called month sin, month costs, and we're going to apply those to the month sin and month costs features. So these are going to compute the sine of the month and then the cosine of the month. The query here contains a selection of features that we want to use to create the feature view from, and then the name of the feature view. So if we go back and have a look at Hopsworks, we can see these were the feature groups that were created. So we had the retrieval one here. And if we look at it, we can see there's a couple of primary keys in it. So there's a multi-part primary key, and then we have the event time when the feature came in, and we can see that they came from different feature groups. So this month cost came from transactions, whereas age came from customers, and garment group name came from articles. With that feature view, you're able to create training data. So you can basically say, hey, I'd like to create some training data. And as new features come in, you maybe create a new train data. So maybe the train data is for the train data up to today. And in a month's time, you want to recreate new train data because more data has arrived. And then you'll create a second train data set. So these train data sets are versioned. And let's have a quick look at how we can create them. So creating a train data set basically means taking a feature view and then calling create training data. Now there is another option that I'm using here called create train validation test split. So what this will do will actually split our training data using, in this case, a random split into train, test, and validation sets. So it's going to be 10% validation data, 10% test data, and 80% in my training set. There is also a time series split. So often in time series data, you might maybe going to use the first year as training data as your training set, and then your test or validation set will be the last most recent month, for example. So you can also do those types of splits. So once we've created some training data, we need to we're going to train our model. So let's look at this. So we're going to use TensorFlow, TensorFlow add-ons and TensorFlow recommenders. In Hopsworks, it's pretty easy if you're training on our platform and working on the platform to install them. You can see here that I installed them already as Python libraries. So if we have a look at TensorFlow, we can see we've got TensorFlow add-ons I installed and TensorFlow recommenders. So this is a Conda environment inside this project that I have, and you can just install and remove libraries from here and customize it. So you don't need to actually manage explicitly if you're running the code in Hopsworks. Now, if you're running this code outside of Hopsworks, and you can do that in any Python environment, then you need to manage the Conda environment yourself, of course. So let's look at what we're going to do. We're going to train the model. We're going to get our training data. And one of the nice things about feature views is you can get the training data, in this case, in training, validation, and test sets. So here we're getting back our features for the training, validation, and test sets, and then the labels for the training, validation, and test sets. So one of the nice things when we create our feature view was that if we look at our feature view for retrievals here, oops, let's look at that. What we can see here is, Okay, let's have a look at one of the other ones. Articles. Okay, so I didn't, you can define a label on the feature group, so it knows automatically which labels include. I don't remember where the label was defined on this. In any case, let's have a look. We'll have to move quickly through this because there's quite a lot in it. But the two-tower model starts here. We have the query tower for our user queries here, and then we have the item tower for the item queries here. And you can see this is our embedding in here. And training it basically involves using this TensorFlow recommenders library. So we have the two towers, and we're going to put them inside the two-tower model. Basically, you take the query model, put it inside this as a member variable inside this two-tower model class, and the item model is a member variable in the two-tower model class. And then we define the training step, what's going to happen. We need to define our loss function there as well. So that's basically the two-tower model. It's not too complicated. Once you have defined your two-tower model, you just define an optimizer on it and then compile it and fit it to your training data. Here we also need to supply a validation data set as well. We're training for 5 epochs, and then we get a model. So then Hopsworks also has a model registry. We can upload that model to the model registry. In this case, we're redefining the interface to the model in TensorFlow. So we have a custom interface to it. So that's why we've done that here with the custom signature to that model. But in Hopsworks, when you upload the model, you'll store what's called a model schema with it. So you'll say, okay, the input schema to the model is this, we take from our data frame that we use to train it. And the output schema in this case is going to be the name of the query embedding, and the embedding is going to be a 32-bit floating point number, and the dimensionality of it we've defined earlier of this embedding. So that's the schema for our query encoder, the user query encoder model. And the same is true for the item encoder model or candidate model that we have here. And then we've now saved both of those models to the model registry. So that's what the two-tower model does. It trains the candidate or item model and the user model. Now we have another program here to write these all of our items to the ANN index, approximate neighborhood index in OpenSearch. And basically what it's doing is it's connecting to OpenSearch here, and we get an index that we're going to store them in, and then we define the operation to write them, and then we're going to write all of the data. So that's what's basically happening here. And it's doing a for loop through all the items to write them, and you can do that as a batch as well. It's slightly more efficient. And then we're going to create a ranking train data set. So the ranking train data set is going to, we have a already defined a feature view called retrieval, and we can jump through here just to look at the model. One of the things about ranking train data sets important is to store both positive interactions and negative ones. Because if you just store the positive interactions where user click on items but they didn't, then the models don't tend to be very stable. So it's important to also have some policy for selecting negative interactions. So that could be just random user item user pairs, because often then you assume that they didn't interact if you pick random ones. Okay, there's a little bit more in this, but basically we train a ranking model. We create the training data set for the ranking model, and then we train the ranking model in here. In this case, the ranking model is a CatBoost model. So CatBoost is it's very similar to XGBoost, but just for categorical variables. So you can see that this is the model here, and then we're going to register it with the feature store again. So here we're registering with feature store. In this case, it's not a TensorFlow model, so we're using joblib to serialize the model itself as a pickled Python object, and then we can save that pickled Python object to to Hopsworks. And then finally, you can create a deployment from it. In this case, we have our transformer that's going to go to the feature store, retrieve the features for the users, go to the open search ANN index to receive similar, to download the closest items to the user query, and then make the ranking call in here. So there's quite a lot happening in there, and you can take your own time to look through it. And the ranking model is the predictor for it is defined here. And then we can create the deployments and deploy them. So let's have a look back at Hopsworks to see where the models are in here. So when we run all of these notebooks, and you can see there's quite a few notebooks. If we go back and look at all the notebooks we've got, you can see there's 1, 2, 3, 4, 5, 6, 7 notebooks, so 7 different steps. We can see here that I've actually selected the feature store profiles. I'm going to change the data science profile. We can see the model registry. So these are the 3 models that I created. If we look at the candidate model, for example, and we can see there's no metrics, so I didn't store it. When you train a model, you may say, the accuracy of it, if it's a candidate model in this case is an embedding, so we don't have any evaluation metric like you would have for a classifier. Maybe you have ranking. In the ranking model, we can see we have precision and recall, which are classifier scores. We also have the F-score. So it's not not the best performing, but with a little bit more data and a little bit more time, you can create a better model. And once you've trained your models, you can deploy them. So these are the K-serve models that are running in deployment. You can see I've got a few of them here. Let me zoom out a little bit. I think I'm zoomed in a bit too much. We can see here we've got our model. We can look at the logs and the metrics, but let's jump into one of the models here. So we can look at this query model here, the deployment. So this deployment is ready and running. You can see then there's no data on it right now, but we have Grafana showing you the latencies of the model number requests per second, and then the type of HTTP response codes. You can see errors if they're appearing here. You can test model endpoints by just pressing run test here. And you can see the endpoint that model is available on. And then real-time logs are available here. You can have a look at them and metrics there. So that's pretty much it. That's what I wanted to cover. I can see we're kind of out, we're running close to end of time. If you have any questions, you're free to write them in the questions box below. Otherwise, I would encourage you to go to Hopsworks.ai, join our Slack community, and you can ask questions. And at Hopsworks.ai, you can create an account and get started within 5 minutes. It really is that easy just to create an account, and it doesn't cost you anything. And then you can try simpler models than this. This is a complex one to get, not somewhere you get started with typically. Typically, you would start with batch applications, but then you can move on to more complex ones.